a staircase, and you're counting the ways up. 100 million recalculations, or 40 additions. Pattern 8 of 10 in the NBX STUDIO Dojo, dynamic programming. The one everybody's frightened of, which is really just refusing to solve the same thing twice. 3 phrasings cover most of it. Number of ways, which is counting rather than listing. Minimum or maximum cost, where you're optimizing. Longest or shortest something. And the real test, can the answer for n be built from answers to smaller versions of n? If the question wants the actual list rather than a count, that's backtracking from the previous pattern. And if a locally best choice is always globally right, greedy is cheaper. Counting, optimizing, and built from smaller answers. Those 3 together mean dynamic programming. You're climbing a staircase of 5 steps, and each move is either 1 step or 2. How many different ways are there to reach the top? Your first instinct is to try every possibility, and for 5 stairs that's fine. Stair 1, stair 2, stair 3, stair 4, stair 5, and the answer comes out at 8. But try that on 40 stairs and your laptop will still be thinking about it tomorrow, because the work doubles with every stair. Every dynamic programming problem needs 2 things, and finding them is genuinely the whole job. First, the base cases, the smallest problems you know without thinking. 1 stair has 1 way. 2 stairs has 2 ways, 2 singles or 1 double. Those are given, not derived. Second, the recurrence, how a bigger answer is built from smaller ones. To land on stair, n you came from n-1 or from n-2. So the ways to reach n are those 2 added, and that sentence is what you hunt for every time. Previous 2 equals 1 and previous 1 equals 2, and those are 2 sticky notes. Previous 2 remembers the stair 2 below, and previous 1 remembers the stair 1 below. Why 2 notes and not a whole table? Because the recurrence never looks back further than 2 places, so anything older can be thrown away. Most people write this with a full array first, which is fine, but noticing you need only 2 variables is what drops the space to constant. The loop starts at stair 3, because 1 and 2 are already known. Current equals previous 1 plus previous 2, so 2 plus 1 is 3 ways to reach stair 3. Then the notes slide forward. Previous 2 takes previous 1's old value, and previous 1 takes the answer we just computed. Previous 2 is 2 now, and previous 1 is 3. That slide is where people slip because the order matters. Overwrite previous 1 first, and you've destroyed the number previous 2 is about to take. Straight from the dojo. Stair 3 takes 3 ways, and stair 2 takes 2 ways. So, how many ways to reach stair 4? 4 ways. 5 ways. 6 ways. Or 3 ways. Have a think, and pause the video if you'd like a moment. Ready? 5, because 3 plus 2 is 5, and every route to stair 4 arrived from one of those 2 stairs below it. Stair 4 is 3 plus 2, which is 5 ways, and the notes slide again. Stair 5 is 5 plus 3, which is 8 ways. That's our answer. 5 stairs, and we did 5 additions. Every stair was computed exactly once, and then only read, which is the whole point of the pattern. Look at the numbers we produced. 1, 2, 3, 5, 8. That's the Fibonacci sequence, and climbing stairs is Fibonacci, wearing a hat. A surprising number of dynamic programming problems turn out to be a famous sequence in disguise, and spotting that's often faster than deriving anything. If you write out the first few answers by hand and the pattern looks familiar, trust it and check it. Here's what dynamic programming saves you from. Written as plain recursion, stair 5 asks for 4 and 3, stair 4 asks for 3 and 2, so stair 3 gets computed twice before we've properly started. Stair 10 costs about 180 calls. Stair 40 costs over 300 million, nearly all recomputing answers the program already had. The loop does 40 additions. Same recurrence either way, because the only difference is whether you write down what you worked out. When a dynamic programming question lands and your mind goes blank, do these in order. Brute force the answers for n equals 1, 2, 3, and 4 by hand. Then ask how each relates to the ones before it, because that relationship is your recurrence. Pin down the base cases. Write the loop upward from them. And only then ask whether the array can shrink to a couple of variables. Order matters because optimizing space before the recurrence is correct is how people burn 20 minutes and end up with neither. For to go and do. Climbing stairs is the one we just wrote. House robber is the same shape with a decision at each step. Coin change moves you from counting to optimizing. And longest increasing subsequence is where the recurrence stops being obvious. 3 things to take with you. The signal is counting or optimizing, built from smaller answers. You always need a recurrence and base cases, and neither one alone is enough. And the saving comes from solving each subproblem once, then only reading it. Next in the dojo is greedy, which is what you get when the locally best choice happens to be the globally right one, and no table is needed at all. Go and do climbing stairs first.